Welcome to AI Paper Podcasts. We are jumping straight into a massive new release from researchers at Korea University called Teaching Language Models to Think in Code. Standard Tool Integrated Reasoning, or TIR, awkwardly interleaves English text and Python execution, leading to severe logic gaps.
Right, and the solution introduced here is the THINC framework. It fundamentally restructures the reasoning trajectory by forcing the LLM to use Python as its primary reasoning engine, strictly restricting natural language to one initial planning step.
So here's the rapid summary for the next 60 seconds. THINC4B hits 78.1% on competition math benchmarks. It crushes traditional TIR models and even beats massive 235 billion parameter models.
And crucially, 99.2% of its answers are definitively grounded in code execution.
Exactly. So the paradigm shifts from treating code as a supplemental tool to utilizing code as the native environment for thought.
Right.
Okay, so bringing you in here for the main discussion. If you are an ML engineer building AI agents, you've probably hit the wall with current tool use setups.
Oh, absolutely. I mean, we really need to look at why standard models are failing so badly at this before we can appreciate how THINC actually fixes it.
Yeah, so let's unpack that. The status quo right now is this alternating loop.
Yeah, standard tool integrated reasoning. Basically, an LLM writes a block of text, explains its thoughts, then it calls a Python tool, it runs a script, looks at the output, writes another paragraph of text, and just kind of repeats that.
Which sounds fine in theory, but the paper points out three massive structural flaws with doing it that way.
Yeah, referencing figure 1 in the paper, the first flaw is what they call post-hoc verification.
Which is basically the model faking it, right?
Kind of, yeah. I mean, the model actually solves the math in natural language first. It figures out the answer in English, and then it just writes a perfunctory Python script to confirm what it already decided.
Right.
It completely wastes the interpreter. Like, we're asking an autoregressive text generator, which is just predicting tokens, to do complex deterministic logic in its head.
Yeah, an LLM is not a state machine. It doesn't hold variables in memory.
Exactly.
All right.
So when you let it compute in English, you're just inviting hallucination.
Which leads right into their second point, unreliable natural language computation.
Yes. So imagine the LLM makes a dumb arithmetic error in that English text block.
Like saying 2 + 2 is 5.
Right. It takes that wrong number, that 5, and hard codes it into the very next Python block.
Oh, wow.
Yeah. So the interpreter runs flawlessly, but the inputs are already corrupted. The Python runtime can't catch the error because it's just baked right into the script.
So the logic error happens before the code is even executed.
Exactly. And the third flaw is what they call misallocated roles. The model writes out this whole step-by-step algorithm in text, and the code just blindly transcribes it. It puts the cognitive load on English, which is, highly vulnerable to cascading errors.
I always look at current TIR models like a micromanaging boss interfering with a really skilled accountant.
Oh, I like that.
Right, like the boss is the natural language part. They insist on doing the math in their head. They write the wrong number on a sticky note, hand the accountant a calculator with the wrong numbers already typed in, and then demand they hit equals.
Yes, that is exactly it.
And when the audit fails, they blame the calculator.
Exactly. But the failure was the boss's mental math all along. We are relying on a fluid, probabilistic, medium English to do a deterministic job.
So we basically need to fire the micromanager.
That is exactly what the THINC framework does. If the micromanaging text is the problem, they just restructure the whole process to eliminate it.
So how does that actually look in practice?
So under THINC, the model gets exactly one thought block, just a single think tag at the very beginning of the prompt.
Wait, literally just one?
Just one. And it is strictly for high-level strategic planning, like framing the search space or doing structural setup. It does zero numerical computation.
None at all.
None. And once that thought block closes, the English reasoning channel is permanently shut off. Yeah, every single step after that is a Python block, followed by the environment giving back a result block. Pure execution loop.
Okay, I have to pause here. Because if you're an ML engineer listening to this deep dive, you know that standard Python interpreter calls are basically stateless.
Right.
Or at least the LLM has to bridge its own context between turns. So if the model isn't allowed to write English paragraphs to explain to itself what just happened, how does it get from step 1 to step 2?
It's forced to rely entirely on the result output.
Okay.
It reads the deterministic output of that previous block, whether it's a number, an array, or an error traceback, and writes the next code block based purely on that.
But how does it keep its train of thought?
It uses inline Python comments. The internal monologue literally happens inside the code syntax, so it tracks its logic using hash symbols, essentially.
Ah, okay.
And because it has to reconstruct its state from the raw output, every intermediate value is verified by construction.
That is wild. But I mean, you can't just prompt an off-the-shelf model to be that disciplined, right? If I tell a standard model, only use Python comments, it's going to break character after like 2 turns.
Oh, 100%. It'll just revert right back to English. You need a highly specific training pipeline to actually teach a model to think natively in code like this.
So let's get under the hood. The paper outlines a 3-stage training recipe.
Yeah. Stage 1 is distillation. They took a really powerful teacher model, Qwen 3.527b, and gave it a strict 3-shot prompt to generate about 12,200 code-centric trajectories.
And they filtered that data set pretty aggressively, right?
Extremely aggressively. If there was any interpreter error, they tossed it out. If the initial thought block was too long, they tossed it. They only wanted pure code-first reasoning.
Perfect behavior only.
Exactly. Then comes stage 2, supervised fine-tuning, or SFT. They trained Qwen 3.1.7b and the 4b model on that distilled data set.
Okay, I actually have some pushback on this stuff.
Let's hear it.
Stage 3 is reinforcement learning, right? That's where they use verifiable math rewards to optimize the model.
Right.
So if RL is ultimately what optimizes for the correct math answers, why bother distilling 12,000 trajectories for SFT? Why not just jump straight to RL and let it learn?
It's the cold start problem. RL is basically rocket fuel for optimizing behavior. But it's really bad at discovering complex formats from scratch.
Because the search space is too big.
Exactly. If you just give a base model a reward, like a 1 for the right answer and 0 for the wrong one, the chances of it randomly exploring its way into a strict Python-only comment-driven syntax are basically 0.
Ah, okay, so the SFT isn't making it smarter.
Right. SFT doesn't teach the model to be smart. It teaches the format. It's behavioral prior. In fact, THINC 4b's accuracy actually drops after SFT.
Wait, really? It gets worse?
Yeah, it drops down to 48.1% because it's being forced into this totally unfamiliar medium.
Wow, okay.
But once that formatting prior is locked in, then the RL phase kicks in. They use group relative policy optimization, or GRPO.
And GRPO is great because it uses verifiable rewards, 1 for correct, 0 for wrong.
Exactly. Over 3 stages, they expanded the context window up to 32,000 tokens and allowed up to 40 tool calls per problem. And that RL phase drives a massive 30-point accuracy gain.
Without breaking the trajectory structure.
Exactly.
Okay, so we know the training works in theory, but let's talk about the results. Because forcing a model to use Python is a cool trick, but how does it stack up?
The results are pretty staggering. THINC 4b hits an average of 78.1% across 5 competition math benchmarks.
We're talking AIM 2024 to 2026, HMMT 2025, beyond AIM. Serious benchmark.
Very serious, and it easily beats heavyweights like R*2, A*, Retool, and the craziest part, it outperforms the massive Qwen 3.235b model.
That is insane to me, a 4 billion parameter model beating a 235 billion parameter model.
It really challenges how we think about scaling laws. Huge parameter counts are great for memorizing world knowledge, but math reasoning doesn't scale if the underlying mechanism of English token prediction is broken. By moving the reasoning to a deterministic environment like Python, the 4b model just punches way above its weight class.
But, okay, let me play devil's advocate. How do we know it's actually thinking in the code? Couldn't it just be secretly calculating the answer in its hidden states and then writing a script that spits that answer out?
That's a great question, and the paper actually proves it's not faking it. They highlight 2 incredible stats. First, THINC averages 349 lines of code per trajectory.
Wow.
Yeah, that's more than triple most baseline models. It's writing full-on software packages to solve these math problems.
And the second stat?
The code-grounded answer rate. 99.2% of THINC's final answers perfectly match a value generated in the interpreter output.
99.2%. That is the ultimate show your work test.
Exactly. Baselines like CORT or ASTER hover below 50% on that metric. For THINC, it's literally impossible for it to cheat and guess in natural language.
It has to compute it. That's amazing. But, I mean, coding is full of errors. I write bugs all the time.
We all do.
Right. So this seems like a massive vulnerability to me. If standard models hit a bug, they can use English reasoning to say, oops, I got a key error. Let me rethink my approach.
Yeah, the natural language safety net.
Exactly. So without an English channel to vent in, doesn't THINC just crash and burn on the very first bug?
Counterintuitively, it's actually more robust.
Really?
Yeah, the researchers tracked its error recovery rate. Even after 3 consecutive code failures like the Python interpreter throwing tracebacks 3 times in a row, HINC, recovers 64 to 69% of the time.
That's incredible. And standard interleaved models.
They completely degrade. They start hallucinating, talking themselves in circles in English, and eventually just collapse.
So how does the HNC actually debug without English?
The paper gives a really cool case study. They walk through 8A126 problem 3. It's a complex algebra problem.
Okay, walk me through it.
So the initial think block just frames the algebra problem into a search space. No math, just structural setup.
Right, setting up the boundaries.
Then in turn 1, it writes a Python block that's basically just brute force search. It writes a nested for loop.
Classic.
Exactly. But it runs it. And in turn 2, it realizes the loop bound is inefficient. So it uses this mathematical concept called monotonicity.
Meaning the function only goes in one direction, so you don't need to search forever.
Precisely. Once you hit a certain value, you can just break the loop early. The model explicitly writes a Python comment noting this monotonic property, and then it self-corrects the loop bound in the code.
So the debugging happens entirely inside the comments.
Yes. Then in turn 3, it implements a parity sanity check, basically checking if the variables are even or odd to filter out bad candidates.
Nice.
And then turn 4, and this is the best part, it independently rederives the answer using a completely different method strictly in Python just to make sure it didn't get a false positive.
That is so rigorous. And they proved this isn't just a math trick, right?
Yeah, they tested out of distribution on the GPQA Diamond Science benchmark, physics, chemistry, biology, and it generalized beautifully.
Wow. So treating code as an external tool is basically the old paradigm now.
Absolutely. Treating code as the native reasoning engine is the future.
I mean, if you are an ML engineer listening to this deep dive, you drastically reduce hallucination when you force the model to operate in an environment where logic literally has to compile to proceed.
It's a total game changer for agent architectures.
It really is. And, you know, the researchers focused on math and physics for this paper, but I want to leave you, the listener, with a final thought to ponder.
Oh, I like where this is going.
What if we applied this thinking in code framework to something completely different, like constitutional law or corporate compliance?
Oh, wow.
Right. I mean, legal systems are essentially just vast, interconnected state machines of logic and precedent.
Yeah, they really are.
So could an LLM use a domain-specific logic language to completely replace natural language arguments?
Just compiling legal reasoning like software.
Exactly. A contract or a compliance check either compiles cleanly or it throws an explicit error traceback. It completely changes how we might handle complex logic. Just something for you to mull over as you build out your next generation of tools.
Fascinating stuff.
It really is. Well, thank you for tuning in to this Breakdown on AI Paper podcast. Catch you next time.